this is our AP Chemistry Chapter 13 lesson video, and this is part 1. In this part, I'm going to cover section 13.1 through 13.3. So let's go ahead and get started. So we're starting again with solutions. So again, if you took honors already, a lot of this should be reviewed, but there will be some new things thrown in. So the solution process. A solution is a homogeneous mixture. The solvent is present in the largest amount. The solute or solutes are the other components. Aqueous solutions have water as the solvent. So R should not be here. Oh well, typo on my part. Solutions can be solids, liquids, or gases. So for example, sterling silver is a solid solution. It's a homogeneous mixture of metals, or an alloy. An example of liquid solution would of course be something like Windex. We use lots of liquid solutions in lab and chemistry. And then of course gases can also be solutions. For example, air is a homogeneous mixture of lots of different gases. So the ability of substances to form solutions depend on two factors: the intermolecular forces involved and the tendency of the substance to spread into larger volumes. So when we decide whether or not something will dissolve into a solvent, we need to take these factors into consideration. And mainly we will focus on intermolecular forces. But of course the tendency to spread into larger volumes, we'll talk about that in a minute. That deals with entropy. So intermolecular forces. Hopefully you're good at these by now, but we'll do a little review. So ion-dipole forces are present when ionic substances dissolve in water. So I'm going to go back real quick. So remember, that's the famous picture that I keep referring to, where an ionic solid dissolves in water and the water molecules surround, and the hydrogens are attracted to the negative ions and the oxygens are attracted to the positive ions, because water molecules of course have a dipole moment, but the ions themselves have a full charge. That's just referred to as an ion-dipole force. Dispersion forces, or London dispersion forces, are present when nonpolar substances form solutions. Okay, now remember, dispersion forces are present even when there's dipole-dipole or hydrogen bonding, but that's the only force present if there's nonpolar. Solutions form when the attractive forces between the solute and solvent particles are comparable to the forces that exist between the two solute particles or the two solvent particles. So what that means is, obviously, the positive and negative ions are attracted to one another. And we know that water molecules are attracted to one another through hydrogen bonding. So if the water molecule wouldn't have a comparable attraction to the ion, then that substance will not dissolve. Now, if it will have a comparable attraction, then it will dissolve. So you know we talked about in honors, like dissolves like, so we'll go back over that. Solvation is the interaction between the solute and solvent particles. So of course that's, like we said, my same picture over and over again of water molecules surrounding ions. Hydration is the interaction between the solute and solvent particles when the solvent is water. So solvation is just any attraction between solute and solvent. If it's particularly water as the solvent and a solute, then we call it hydration, because of course water is involved. So our delta H for solution is your delta H 1, 2, and 3 added together. So those are the change in enthalpy of 3 different processes. So delta H of solution is the energy change when the solution forms. Delta H1 is the energy required to separate the solute particles. So since energy is required, that will be endothermic. It'll be a positive value because we're taking solute particles that are attracted from each other and we're pulling them apart. Delta H2 is the energy required to separate the solvent particles. So again, since it's required, that's going to be a positive number. So if we're talking about the solvent as water, we need to break the hydrogen bonding between the water molecules. And then delta H of 3 is the energy released when the solute and solvent get to attract. So because it's released, that's going to be exothermic and have a negative value. So this is what's happening. We have the solvent, it's spreading out. That is an endothermic process. We have the solute, it's spreading out. That's an endothermic process. But then when the solvent and the solute get to attract, that is an exothermic process because that's thermodynamically favorable. So will a solution form? How do we know? Processes that are exothermic tend to be spontaneous or thermodynamically favored, but endothermic processes still occur. So why is that happening? So for example, ammonium nitrate spontaneously dissolves in water even though the delta H of solution is a positive 26.4 kilojoules per mole. So that means that it can't just be based on enthalpy, which is of course our delta H. So what else is it based on? Well, spontaneous processes involve two factors: energy, which is our delta H, and exothermic is thermodynamically favorable. But it's also what I said a minute ago, that tendency to spread out. So where is that coming from? Well, that's our entropy. So if you took honors, we discussed this. Entropy is the degree of randomness or disorder in a system. Processes in which the entropy or randomness of the components increases tend to be spontaneous. So if we can increase the disorder or the randomness, then that is a favored process. So the formation of solutions involve enthalpy, which is your energy change, and entropy, which is your randomness. So if you watch in the beginning, the blue particles, they're very close and orderly. But as it dissolves, they become random and spread out. And so as this dissolves, there's an increase in that entropy. So even if it's not favorable by energy change, it might be favorable by entropy change. So let's look at our first sample exercise together. So it says, the picture below shows the following reaction. We have solid sodium sulfate, and we have water vapor. And it's in kind of a covered, like a beaker put upside down. Well, not a beaker, because then you would have the little lid. But it's in a container, closed container. And what happens is this crystal absorbs the water and becomes a hydrate. So essentially all the water vapor in the container is consumed in this reaction. So that's what's happening. So it says, if we consider our system to consist initially of our solid and our water vapor, A, does the system become more or less ordered in the process? See how if you look, right here, we got the water vapor all over the place. Here, everything is nice and tight and all packed together. So this is more orderly. Okay, so it becomes more orderly because we're going from a gas, which is all over the place, to an orderly solid. So then it says, does the entropy of the system increase or decrease? Well, entropy is the amount of randomness or disorder. So if we're getting more ordered, then our entropy decreases because it's getting more orderly. All right, so you try this one real quick. I'll assume you paused it, tried it, and we'll look at it together. It says, does the entropy of the system increase or decrease when the stopcock is open to allow mixing of the two gases in the apparatus? So here we have all our nitrogen on the left and all our oxygen on the right. But when we open this stopcock, they're allowed to mix together. So see, before we started, it was very orderly. I have nitrogen on one side, all my oxygen on the other. Once I open that stopcock, they all mix together. So what happens to the amount of entropy? It increases. Because of course those gases are going to mix and become disordered. All right, so let's look at section 13.2. We're going to talk about saturated solutions and solubility. So dissolving and crystallization are opposite processes. So when you have a solute and a solvent and they're separate, and then you mix them together to form a solution, that is a dissolving process. Okay, so if I have my solute, put it in there, it's allowed to dissolve, that is my dissolving process. However, you can have a crystallization. That's when you have your solution, but you allow it to split. So for example, like a supersaturated solution, if you add that extra crystal, some of it will crystallize out. So solubility can be expressed in the solubility curve. The maximum amount of solute that will dissolve in a given amount of solvent at a specified temperature is the solubility. So you can see most solids, they increase in solubility as temperature increases. Okay, not every single one does, but most of them do. So an unsaturated solution contains less than the maximum amount of solute at a given temperature. So if you add more solute, then it will continue to dissolve. Okay, because it's not saturated, it's not full yet. A saturated solution contains the maximum amount of solute at a given temperature. So if you add more solute, it will not dissolve, it's just going to settle at the bottom. And you can stir, stir, stir all day long, and it might seem like it dissolves because it'll kind of float around for a little while, but then it's still just going to come back and settle at the bottom because it's already saturated, so it can't hold anymore. It's reached its solubility. A supersaturated solution contains more than the maximum amount of solute at a given temperature. So you may think, well, how in the world is that possible? Well, remember, solubility is based on temperature. So a supersaturated solution is made by heating the solvent to a higher temperature so that you can dissolve more solute. Then, if the solution is carefully cooled, it will prohibit the crystallization from occurring. And so then you have more than the maximum. So you have a supersaturated solution. Now, of course, that is incredibly unstable. So if you add more solute, then what happens is crystallization occurs. So you'll notice my solute gets bigger. So I showed you an example of this in class. So supersaturated solutions are extremely unstable. A little piece of dust falling in sometimes can cause crystallization. All right, so section 13.3, factors affecting solubility. The stronger the attractions between the solute and solvent molecules, the greater the solubility. So polar solvents tend to dissolve polar or ionic solutes. Okay, so this is where that whole like dissolves like comes from. And nonpolar solvents tend to dissolve nonpolar solutes. And like I said, we sum that up as like dissolves like. So polar can dissolve polar or ionic, nonpolar can dissolve nonpolar. So liquids that are miscible will dissolve one another. Examples are water and rubbing alcohol. Liquids that are immiscible will not dissolve one another. Examples are water and oil. And of course, that's because of those intermolecular forces. Water's polar. Oil, which is usually long chains of C's and H's, long hydrocarbon chains, they are nonpolar. So that's why they don't want to mix, because polar will dissolve polar and ionic, nonpolar will dissolve nonpolar. All right, so hydrocarbon molecules. CH bonds are considered nonpolar due to the small difference in electronegativity. Hydrocarbons tend to be insoluble in polar solvents. So if you see those long CH chains, consider that nonpolar, because even most of the time the tiny dipoles that are even possible between C and H cancel out due to the geometry of the molecule. So hydrocarbons tend to be insoluble in polar solvents. One way to increase the solubility, though, is to add a polar group. And most of the time, that'll be an alcohol group or an OH group. Okay, so if we just have a whole bunch of C's and H's, it's going to be nonpolar and not dissolve in water. But if we can switch out one of those H's for an OH group, that can form hydrogen bonding, which is similar to intermolecular forces in water, so it's more likely to dissolve. As the carbon chain of an alcohol increases, the solubility decreases due to the increased London dispersion forces. The molecules start to act more nonpolar. Okay, so see here I have C, 3 H's, and an OH. So not most, but a large portion of the molecule can form hydrogen bonding. But if I have a super long chain of CH's, what I want you to notice is most of this molecule is nonpolar. Only a tiny portion is polar. So this would be more likely to dissolve in water than something like this because of this huge nonpolar chain. The more of a molecule that's nonpolar, the less likely it is to dissolve in polar. Network solids are not soluble in polar or nonpolar due to the fact that they're not made of intermolecular forces. They have strong covalent bonds throughout. So let's look at our first sample exercise. It says, predict whether each of the following substances is more likely to dissolve in the nonpolar solvent carbon tetrachloride or water. Okay, so let's look at this one together. So we have carbon tetrachloride, which is just CCl4, and it went ahead and told me it's nonpolar, although I should be able to easily figure that out because when you draw it, it'll be tetrahedral, all your dipoles will cancel, or water. So we know water's polar. We already know that, partial positive, partial negative side. Okay, so remember, nonpolar can dissolve nonpolar, polar can dissolve polar or ionic. All right, so first it gave me C7H16. So remember, this is a hydrocarbon. It's made of carbons and hydrogens. It's going to be nonpolar overall. So I'm going to put that under my carbon tetrachloride. Sodium sulfate. Well, remember, when you see a polyatomic ion, that means to make you think ionic. Okay, so polar will dissolve polar or ionic. HCl. HCl is going to have a dipole moment. Okay, Cl is closer to F than H, so it's going to do like this, and it's not going to cancel out. So that will have a dipole moment, so it's polar, so it will dissolve in polar water. And then I2, that's going to be nonpolar because it's just two iodines attached together. So that will have London dispersion forces, which would be similar to other nonpolar substances. All right, so that's all you have to do for deciding if things will dissolve in one another. Alright, so you try the next one. I'll assume you've paused it and done it, and we'll look at it together. So it says, arrange the following substances in order of increasing solubility in water. So I'm just going to call it 1, 2, 3, 4. Okay, so 1 is not very soluble, 4 is really soluble. So here we have a whole hydrocarbon chain, just a bunch of C's and H's. This is going to be nonpolar, so it's not interested in dissolving in water. So this is going to have a very low solubility. If you look at the difference in the other ones, we have some OH groups, and we have a Cl here, okay? Well, once you add that Cl, this area right here becomes polar. okay? And so that, of course, can have dipole-dipole attractions, which are more similar to water than London dispersion or nonpolar attractions. So this would kind of be soluble, okay, because of that CO group. But once you add an OH, now you have hydrogen bonding as an option. And so that's going to be more similar to water, so this would be even more soluble. But this one has 2 hydrogen bonding locations. So water is going to like that one even more. So this would be the most soluble, okay? So if you look, I put my order down here. So we start with our C5H12, next is the one with the Cl, next is the one with the OH, and last is the one with the 2 OHs. So the more polar portions of a molecule, the more soluble it will be in something that it is polar. Alright, so the solubility of liquids and solids are not affected by pressure, but the solubility of a gas is affected by pressure. The solubility of a gas increases when pressure is increased. Okay, so normally a gas will just want to bubble out of a liquid. So if you force the gas into the liquid, if you apply pressure, more of it will dissolve into the liquid, increasing the solubility. So for a solid, you want to increase temperature to make it more soluble. For a gas, you want to decrease temperature and increase pressure to make it more soluble. So Henry's law shows the relationship between pressure and solubility of a gas. It's S sub G equals K times P sub G. So S sub G is just solubility of a gas in molarity. K is Henry's law constant. It's different for each solute-solvent pair and changes with temperature. And it has kind of weird units. It's moles per liter times atmospheres. And then P sub G, hopefully you can read that right there. It's right here. P sub G is the partial pressure of the gas in atmospheres, of course, because you need your units to match here. All right, so let's look at one together. So it says calculate the concentration of CO2 in a soft drink that is bottled with a partial pressure of CO2 of 4 atm over the liquid at 25 degrees Celsius. The Henry's law constant for CO2 in water at this temperature is 3.1 times 10 to the negative 2 moles per liter times atmospheres. All right, so we know that Henry's law says S of my gas is K, P of my gas. So then I just plug in. So they told me K, Henry's constant, is 3.1 times 10 to the negative 2, and that's moles per liter times atmospheres. And we multiply it by our partial pressure, which is 4 atm. So if you look, my atm cancel, I'm left with moles per liter, which is perfect, that's just molarity. So once I multiply the two, I got 0.124 molarity. Just like that. Super easy, we didn't have to convert anything. Alright, so on the next slide, I will go ahead and tell you, I think you need to use the same Henry's law constant, so you may need to click back here, because I think the next part deals with a similar situation. We're just changing the pressure. Alright, so you try the next one. I'll assume you've tried it, and we'll look at it together. So it says, calculate the concentration of CO2 in a soft drink after the bottle's open, and equilibrium is established at 25 degrees Celsius under a CO2 partial pressure of 3 times 10 to the negative 4 atm. So see, we still have CO2 in water, so we're going to pull that same K value from the previous slide. So remember, our solubility of the gas is K times partial pressure of the gas. So our K from the last slide was again 3.1 times 10 to the negative 2 moles per liter times atmospheres. But this time our pressure has decreased to 3 times 10 to the negative 4 atm. It was 4 atm on the last one. So my atm's cancel, I'm left with moles per liter, which is molarity. And so I got 9.3 times 10 to the negative 6 molar. Just like that. Alright, so hopefully that was pretty easy. I mean, it should have been. You're just multiplying two numbers. Alright. So temperature. The solubility of most solids increases as temperature increases. So you can see how as temperature is increasing on our x-axis, you can see most of our lines are curving or pointing upward. The solubility of most gases, on the other hand, decreases with increasing temperature. Because you have to think, we want gases to be cold to slow the particles down so they're more likely to stay in the liquid. The faster they are, the more likely they want to escape and just become a gas. Alright, so that is the end of the first lesson video. So pretty much really the only new thing from honors was that Henry's law, and that was about it. So hopefully the rest of it you remember from honors.